So now we will have a look at the analysis of the coated nanoparticles with the PTFE core. I have the data in number 16 here, and we have PMMA here and PS polystyrene. And they're both lower coverage spectra, which means we have a sub-monolayer of the nanoparticles on a silicon wafer. Look at the PMMA first and analyze that. I have, as you can see, the already cut out the fluorine 1s here, fluorine and fluorine OG. So we only have fluorine in this wide energy range here of 200 eV. So we analyze that. We need an IMFP. So we have a peak energy here of 800. So we set the energy at 800, and we look for CH, looking for polymer, and we have a lot to choose from here. Need the value for the IMFP at 800 eV. It's about 23 here, and it's about 23 for all of them. So we just take 23. So we just put in 23 for the IMFP here, 23. And we have polymers, so we use the polymer cross-section. We have the PTFE core, which was fairly thick. So we are just looking at the fluorine, the PTFE core, covered with the PMMA in this case. And we find the thickness of the coating, and you see with about 40 or 50, we have a good account for the background here in a white range. It's not so good here. So this probably means that this is not the right structure, but this 45 angstroms, 4.5 nanometers, would probably give us a rough indication of the average thickness of the coating. But if we now change the structure to include the possibility to have different coatings across the surface, we have that here, this possibility here, we can maybe get a better account here. And I'll just see what we get here. You see, something like this is clearly better. It's still not perfect, but it's better, right? So probably what we have is two different coatings on the surface. One small coating and another part which is coated which has a larger coating. This would correspond to the core of the nanoparticle to be off center, and then we'll have some situations where it's sticking upwards and other where it's sticking downwards, and they have the where we are exposed to the larger thickness. If we do the same for the polystyrene, we have again for the buried layer, we get something similar, maybe a little bit less. We have a very good count here, but not in this range. So we have about 4 nanometers for the coating, but the coating is non-uniform. As you can see, if we change to this structure, we get a better account for the background. Something like this, right? Something like this. So we clearly have coatings that are off-center. You'll note that the fit here is not perfect. That's because the plasmon here is a little bit off, and we can adjust that as I'll show in the next video. We could improve on this analysis. You see the plasma here is not lined up with the precision in the experiment. So the universal cross-section for the polymer here, for the polymer we're looking at, it seems to have a little bit different plasma energy. We can try to improve on that by simply changing to an external cross-section and manually find a better fit. So we have to line it up with that. So maybe like this, it lines up here. It's much wider. So we widen it up a bit, maybe about here, and fine adjust these numbers. So it's about here, right? And if we change the height here, so we have the uncovered part here of the core, and if we increase that by 0.5 nanometer, this is clearly worse than without. So it's really sticking out. The core is sticking out, and this is in the backside of the coated nanoparticle that has this 7.5 nanometer height. We can do the same for the PMMA with the new cross section, and here we probably get something like this, and maybe a little bit thicker here, and maybe less here, like this, like that. So it's about here, right? So here it's also very much off center, the core, but it's still coated on all sides. We can try to see if we can improve this even further. If we can get a better cross section, maybe we can fine adjust the determined structure. To do that, we could use a pure PTFE spectrum. So here is the spectrum from pure PTFE, the core of the nanoparticle. So the idea here is that we know this is pure, so we know the structure, and then we fine adjust the cross section so that it accounts very well for the structure here. So it's already quite good out here and out here, small things here, so we're very close already by the manual adjustment as we did before. We will now look closely at this region and get a better fit. So if I change the C value here, it moves it a little bit further out. So that's about better here, 850. And with D, maybe that should be a little bit more narrow. We could also, the PTFE has a band gap, and you also see there's some mismatch here. So let's just try to put in a band gap here to make the fit even better here. And something like this seems to give a very good fit then here, over here, and so on. Let me put this at 20 and then maybe fine adjust the values. So this is very close now. So we just use this cross section now for the analysis. So I go back and look at the polystyrene here. This is what we had, the active substrate here. And we had two regions with roughly these numbers. Like this, and now you see it's very, very good. So this gives a little better confidence in the values, but I don't think it really gives a difference in the analysis. So now you see this is very good fit everywhere. So it's the uncertainty on these numbers is very low, as you can see. And we can take the other one, the PMMA, and again have a look at this. Here we found 15 here, I believe, and a smaller coverage here, around here. So you see we get about the same, but we get a better quality of the fit, so we have better trust in the numbers we find. The uncertainty is smaller than. Yeah, this is the best fit here, right?